Hello everyone, today we are continuing our trigonometry unit with section 3, which is going to talk about solving for angles and angles of elevation. So it says right here, previously you learned that sine of 30 degrees is equal to 0.5, or 1/2. Therefore, if you know that the sine of an acute angle is 1/2, you can conclude that the angle was 30 degrees. We worked backwards to solve. This is known as the inverse sine, which can be written as, and I'll zoom in here so that's nice and clear, sine to the -1 power of the opposite over the hypotenuse as our function. So the ratio of our sides is inside now. Before we had our degrees, our angle measure in here. But when we work backwards, we're solving for the angle measure. And this is equal to angle measured in degrees for right now. All right, so for example, using the one that is in the problem here, it says the sine of 30 degrees is 1/2, then we could say that the inverse sine to the -1 power of 1/2, 1/2, is equal to 30 degrees. This would be an example for you. So now that we've talked about what an inverse sine is, we're going to use our calculator to solve for inverse cosine, inverse sine, and inverse tangent. We're going to switch to another video where you can see better what buttons I'm pressing on the calculator, and then we'll come back here and move on. In this video, I'm going to show you how you can use the TI-84 Plus graphing calculator to solve for inverse cosine, inverse sine, and inverse tangent. So a lot of this works similarly to the cosine, sine, and tangent functions, where you still need to make sure that your calculator is in the degree mode, which mine is, so I'm going to leave it. And then where our sine, cosine, and tangent buttons are, I'm going to tilt my calculator so you can see a little better. There's blue letters right above them that say sine to the -1, cosine to the -1st power, and tangent to the -1st power. And those are our inverse functions. So we have inverse sine, inverse cosine, and inverse tangent. In our first example, we have cosine, our inverse cosine of 0.87. So I'm going to hit the second key, then I'm going to hit the cosine button, which is selecting where these blue letters are, the inverse cosine function. I'm going to type in my ratio, because the part that goes here in our inverse function is the adjacent over hypotenuse ratio, which in our first example is written as 0.87. We're going to close the parentheses and then hit enter. And that tells me that the angle that I was solving for is going to be about 29.5 degrees. The second example, we have the inverse sine function, and this function is again second above sine. That selects the inverse sine, and we have 0.43 in our example. Close the parentheses, hit enter, and that tells me that the angle I was solving for is about 25.47 degrees. We also have the inverse tangent function. I'm going to again hit second, then the tangent button to select inverse tangent. Our example has 0.71. We're going to close the parentheses, hit enter, and that tells me that my angle is about 35.37 degrees. All right, so we just figured out that the inverse cosine of 0.87 is 29.54, the inverse sine of 0.43 is 25.47, and the inverse tangent of 0.71 is 35.31. So now we're going to go ahead and move to example 2, which says to use the figure to the right to A, find the measure of angle A, and B, find the measure of angle B. And to do this, it's going to help us if we can see our acronym SOHCAHTOA on the side. I'm going to write it on the edge over here. So I have sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. There's our acronym, SOHCAHTOA. And if I'm looking at angle A, and I'm trying to solve for angle A, and I know AC and AB, well, AB is the hypotenuse. The relation to angle A with this side is that it is adjacent, it's next to. So which function uses both the adjacent and the hypotenuse? So if I come over here, we have three options: sine, cosine, or tangent. Cosine uses adjacent and hypotenuse, which is what we have, so this is the only function that we can use to solve for our missing angle A. But remember, we're solving for the angle, not the ratio. Because we're solving for our angle measure, we're going to use an inverse function. So I'm going to need inverse cosine. So the inverse cosine of the adjacent, which is 12, over the hypotenuse, which is 13. 12 over 13 is equal to our angle measure, which is angle A. Now we're going to take this and we're going to plug it into our calculator. So I'm going to pull that up here. And I have second cosine, 12 divided by 13, close my parenthesis. 22.619, that rounds to 22.62 using 2 decimal points. So angle A is about equal to 22.62 degrees. All right, so now we want to find the measure of angle B. I'm going to move my calculator to the other side if it will let me. There we go. And let's look at this triangle again. So this time we're solving for angle B. Angle B in relation to this side is opposite, but this is still the hypotenuse. So now for angle B, we want something that uses the opposite and the hypotenuse. So if I come look at my options, sine, cosine, and tangent, sine uses the opposite and the hypotenuse, so that's the function that we need to use. It's the only one that uses both the opposite and the hypotenuse. So the inverse sine will solve for our angle, and we need an opposite over hypotenuse. So we're looking at the inverse sine of 12 over 13. Now let's go over here and write that down. So I have the inverse sine of 12 over 13 is equal to the measure of angle B, which means after we type that in our calculator, it's probably going to be another approximation. So let's type this in. Sine, the inverse sine of 12 divided by 13, close the parenthesis, is 67.38. And that is my approximate measure of angle B. All right, I'm going to put my calculator away for a little bit here. We'll bring it back when we need it again in just a moment. All right, so that is how we're going to find our angle measures. You do need to be careful with how you're rounding to make sure that you're as close as possible. This is an approximation. If you are needing to continue to solve, let's say you're looking for side CB, then it would be better to use an angle measure that you already know. The only thing is, in this case, we solved for both A and B, and both of them are approximations. So you're just going to need to pick one of them, use 2 decimal points, and know that whatever answer you would get is going to be an approximation because you were using an approximated angle. All right, on example 3, it says to find all the angles of the triangle to the right. It's the exact same concept as we did with example 2. What I will mention is that we have all 3 sets of sides, so you can use any function that you want. It's just going to depend on which sides you're using. We used both inverse cosine and inverse sine in example 2, so with example 3, let's purposely use tangent. All right, so if I'm trying to solve for angle B, and I want to use tangent, then I need the opposite over the adjacent, which is 24 over 7. So for angle B, I'm going to set that equal to the inverse tangent of 24 over 7. The other angle we need to solve for is angle A. If I'm using tangent again, we're opposite over adjacent, 7 over 24. 7 being opposite, 24 being adjacent, which is not the hypotenuse. So 7 over 24. So angle A is equal to the inverse tangent of 7 over 24. Now I'm going to plug both of those in my calculator to solve for our missing angles. So I'll pull my calculator back out. So I have the inverse tangent of, for angle B, 24 over 7 is 73.74 approximately. And the inverse tangent of 7 over 24 is approximately 16.26. And both of those are in degrees. So that is our angle measure approximately. All right, now that we've done that, we have two examples left that both ask us to solve for the triangle completely. Because the process is pretty similar to what we've already been doing, we're going to just do example 4 and we'll skip example 5. So in example 4, I have triangle SRT, and I know that angle S is 90 degrees, my hypotenuse is 5.7, and side SR is 5. Now in this situation, we could use the Pythagorean theorem to solve for side ST because we know two of the others and it's a right triangle. Because we're trying to use trig functions, I'm not going to use the Pythagorean theorem, but you could do that as an option. For now, because we want to use our trig functions, I need to start by finding angle T and angle R. So I'm just going to start with angle T. Angle T has angle 5 across the way, that's opposite, and then we have the hypotenuse. So I need to use a function for angle T that is using the opposite side and the hypotenuse. And that function is sine. Sine is equal to the opposite over the hypotenuse. So the sine gives us our ratio, so we need to use inverse sine to solve for our angle. So the inverse sine of the opposite over the hypotenuse, 5 over 5.7, will be equal to T. So angle T is equal to the inverse sine of the opposite, which was 5, over the hypotenuse, which was 5.7. All right, we will come back to that. I'm going to get the other angle ratio written down, and then I'll plug both of them in my calculator at once. All right, so I have angle R. For angle R, the side 5 is adjacent to angle R. So I'm going to need to use cosine because that uses the adjacent and the hypotenuse sides. So I have the inverse cosine of 5 over 5.7 will give me the measure of angle R. So angle R is equal to the inverse cosine of 5 over 5.7. All right, I'm going to take a second and plug those in my calculator. So I have the inverse sine of 5 divided by 5.7. That gives me the measure of angle T. So angle T is approximately 61.31. For angle R, we have the inverse cosine of 5 over 5.7, which means that angle R, oh, I forgot to type in the inverse part. Let's try that again. Inverse cosine of 5 over 5.7 is approximately equal to 28.69. So angle R is approximately equal to 28.69 degrees. All right, so I have 61.31 degrees, and I have 28.69 degrees. I'm now going to use one of those two angles to solve for my missing side, which is ST. I'm just going to choose to use angle T on this one. There's no reason in particular, I'm just choosing that one. ST is adjacent to angle T. That means that we need to use a function that has the adjacent side, and we know both the opposite and the hypotenuse. So it doesn't matter if you choose to use cosine or if you choose to use tangent. But you do need to be careful that you are making sure that you're using the right function with the correct sides. So if I choose to use tangent, then I would have opposite over adjacent. If I choose to use cosine, then I'd have adjacent over the hypotenuse. I'm just going to use cosine for this one, so I have the not the inverse, because we have the angle measure. We're solving for the side length. So we're going to use regular cosine of 61.31 degrees is equal to the ratio of the adjacent, which is ST, over the hypotenuse, which is 5.7. So ST over 5.7. To solve for this, we're going to multiply both sides by 5.7. And that will give me ST, and I'm going to type this 5.7 times the cosine of 61.31 right in my calculator. So I have the cosine of 61.31, close the parentheses, times 5.7 is giving me ST is 2.736. So we're going to say that that is 2.74. So ST is approximately 2.74. We don't have a unit for that, so I'm just leaving it, but you would write units if you needed to label it. Alright, so now that we've talked about how to solve for missing angles, we need to talk about some classification of angles. So we have angles of elevation and angles of depression. An angle of elevation is formed by a horizontal line and a line of sight to a point above the line. An angle of depression is formed by a horizontal line and a line of sight to a point below the line. So if you think about something being depressed, it usually means it's being like squished down. So an angle of depression is going downward. It's the angle you're looking down. Angle of elevation is an angle looking upward. Elevate, you're lifting up. So we are looking upward. That's our angle of elevation. So let's go ahead and write that right in our picture. So I have for angle 2, this pilot is looking down, so we have an angle of depression. And this guy in the tower is looking up, so that is an angle of elevation. All right. So since we know those terms, we now can use those in some story problems in real-world situations. So starting with example 1, classify each angle below as an angle of elevation or an angle of depression. All right, so anything that shows us looking down is going to be an angle of depression. Anything looking up will be an angle of elevation. One important piece is that we need to take perception into account here. So we're looking at point of view. So if this person is looking this way, for him, looking downward would be angle 8. That's referring to this angle here. Whereas over here, we're looking at, from here, looking up at this guy. This is angle 9 over here, so that is an angle of elevation. Angles of elevation are 7 because he's looking up, and here we're looking down, here we're looking up towards that guy, so 9. So angle 7 and angle 9. Angle 7 and angle 9. Right, and then angles of depression occur when our line of sight goes down. So for this guy, looking down would be angle 6. For our observer over here, looking down would be angle 8. So angle 6 and angle 8 are angles of depression. And that's because of where they're starting. So our starting point over here is looking up, meaning 9 is going up. Our starting point over here is looking down, so angle 6 is going down. It also drops down from this horizontal line. That's part of it as well. Example 2 says, suppose a plane is at an altitude of 3,500 feet and the angle of elevation from the airport to the plane is 29 degrees. What is the horizontal distance between the plane and the airport? Round to the nearest foot. All right, so it's going to be helpful for us if we draw a picture here. And I know from my students last year, they gave me the airport coding, the letters, as K, R, G, G. So that's our airport. And somewhere off in the distance, we have an airplane that is flying at 3,500 feet. So we have this airplane. I'm going to do the best I can to draw this here. Okay, there's my airplane. Maybe you can draw a better one. And we're looking for our horizontal distance, knowing that this airport angle of elevation, looking from the airport to the plane, is 29 degrees. And our altitude, or our height, is 3,500 feet. All right, so now looking at this triangle, we're solving for this missing piece here, our horizontal distance, which I'm going to mark as x. All right, so if we're trying to solve for this side here, I know this angle is 29 degrees, and I know this side, which is opposite our angle, is 3,500 feet, then I'm looking for a function that uses the opposite and the adjacent side. In this situation, that is only available with tangent because that's the information we have. We have opposite and we're looking for adjacent. So the tangent of 29 degrees will be equal to the opposite over the adjacent side. So let's go ahead and write that down. So the tangent of 29 degrees is equal to opposite of 3,500 feet over x. All right, so to solve this, we're going to first get x out of the bottom of our fraction by multiplying both sides of our equation by x. That gives me x times the tangent of 29 degrees is equal to 3,500 feet. I still want to get x by itself, so now I'm going to divide out our tangent function. So we're dividing the tangent of 29 degrees out on both sides, which means that x, once we do all that division in our calculator, is about 6,314 feet. So if we're standing at the airport looking up at a 29-degree angle at an airplane that is 3,500 feet in altitude, then it is approximately 6,000 feet away from us. All right, example 3 is a very similar type of question. It says a plane is flying at an altitude of 14,500 feet. The angle of depression from the plane to a control tower is 15 degrees. What is the horizontal distance from the plane to the tower? All right, so in this case, we are in a tower, and let's draw a picture again. So we have this tower here, and the top part has this person in it, and he is looking upward at an angle of 15 degrees at a plane that is flying approximately 14,500 feet. Not approximately, it is flying at 14,500 feet. And we need to draw another plane up here. All right, there's our plane. And we are looking again for that horizontal distance. So we want to know how far in horizontal distance the plane is from the tower. And because we're looking at our line of sight, it is okay to just use this 14,500 feet because we're looking across our line of sight. Otherwise, we would have to add in the height of the tower plus the height of the person up to their eye line. But we can talk more about that another time. All right, so in this situation, because we're again looking for horizontal distance, we need to use the exact same function that we did before. We need to use tangent because we have the opposite side and we're looking for the adjacent side. So I have for this one, the tangent of 15 degrees is equal to opposite of 14,500 feet over our unknown adjacent side, which is x. I'm going to zoom in here again. We're going to solve the exact same way. We're going to multiply both sides by x to cancel out our x on the bottom of our fraction. Then we have x times the tangent of 15 degrees is equal to 14,500 feet. We're going to divide the tangent of 15 out from both sides. We're still in degrees, by the way. And in doing so, that gives me that x, or our horizontal distance, is approximately 54,115 feet. This is where we're going to stop for today. We'll pick back up in section 4 to cover what happens when you have trigonometry in the coordinate plane.